Okay, thanks for the introduction. Hi everyone, I'm Qian. I have a research group approaching 4 years old at Urbana-Champaign. My group has students and postdocs coming from various backgrounds with formal degrees in material science, chemistry, electrical engineering, and physics. So I'll use an analogy to show you how they all got attracted by the research in my group. So historically, the starry heavens above us really serve as the most initial inspirations for scientists, and all the understandings truly started to grow when telescopes were put out there to see them directly. So similarly, on the extreme of small scale, such as inside micron-sized living cell, there are also many vivid events shown here as an animation. Nano-sized cellular machineries travel busily to perform their functions. The dynamics at this scale is what we refer to as the elusive, and this is because for a long time, the nanometer resolving transmission electron microscopy, or TEM, works in high vacuum. So as a result, even if you put a liquid sample in, it will dry out and leave you no dynamics at all. So here comes my group's unique expertise. We have two versions of the emergent liquid phase TEM tool, which can image a liquid sample with nanometer resolution and a high vacuum of TEM. So one is graphene layers sandwiching and seal a liquid sample in between. The other is a microfabricated liquid chamber, which allows in situ TEM imaging and the liquid flow with electric bias. So on this slide, I'll show you different types of nanoscale dynamics we can probe experimentally, which was not possible before. So the first is to study the self-assembly dynamics of differently shaped nanoparticles as shown here. So this is a TEM movie of how nanoparticles assemble one by one into a superlattice. And my group has also developed single particle tracking to do statistical mechanics-based analysis on the aggregation pathways. The second is to see the reaction dynamics on nanomaterials, and this is a movie showing the active deposition of iron oxide at the gas-liquid interface. We can get lattice fringes, we can get electron diffraction patterns to really tell the deposition mechanism. And similarly, we're also imaging and understanding magnesium ion intercalation dynamics and the cycling into nanostructured cathodes for advanced battery design. And then beyond those inorganic materials, in the third example, my group studied how polymer actually develops various nanoscale morphology during synthesis. So here is a 3D reconstruction of a crumpled polymer film together with an element map from which we can extract a synthesis, morphology, performance relationship for its use in water filtration. And the last two examples are on proteins. We're able to see and track the fluctuations of single membrane proteins in liquids as shown in this movie. We are also in the process of imaging biological self-assembly, such as the amyloid fibril formation, which is actually a very bad aggregation responsible for a lot of diseases. So I should comment, this list keeps evolving and expanding. Our capability to really image a liquid sample and the dynamics it carries with nanometer and millisecond resolutions really allow us to study a variety of artificial and biological soft materials in aspects not accessible before. And you might recognize those examples relate to different disciplines such as materials chemistry, soft condensed matter physics, engineering, biophysics, and chemistry. So the unique view for my group to retie all the topics together is to really address the common challenge to see and understand their structure and dynamics one by one directly. And beyond liquid phase TEM, we also use other more conventional characterization tools such as small angle X-ray scattering, optical microscopy, and tomography to really make our understanding more comprehensive. So for today's talk, I'll focus on 4 short stories, and hopefully you can find something that resonates with your own scientific interest. So the first story is to understand the emergence of order for many nanoparticles interacting and assembling with each other. So on the fundamental aspect, we can basically see them as very well-defined model systems to study the physical rules for self-organization on the nanoscale. On the application aspect, each type of nanoparticle and their self-assemblies actually has their own functions to behave as a reconfigurable device. So as shown in this hypothetical phase diagram here, they can actually arrange and then rearrange to sample their own energy landscape in response to external environmental stimulus such as pH, temperature, or external field. However, the current status of the field is actually a knowledge gap. So on the left is a 2016 review paper on the beautiful variety of nanoparticle superlattices. Yet those are just single snapshots. You mix things at the very beginning and then check the end product using electron microscopy. And this approach is fundamentally disconnected with the other prospective paper published in 2015, while quite some fundamental questions of crystallization are still unknown. For example, people actually speculate the nanoscopic building blocks will go through intermediate phases instead of a classical nucleation pathway towards a final crystallization. And this is very important to determine the crystal properties, but this cannot be experimentally explored from just single snapshots. So a natural solution we realized was to really just utilize liquid phase TEM to see the crystallization in real time and also in real space. So this idea sounds very obvious and straightforward, yet it didn't take us long to realize how naive we were. That's because there are complications. So nanoparticles were repeatedly shown by others to react and change their shape under the electron beam of liquid phase TEM. While this is wonderful to re-understand nanoparticle goals or corrosion mechanism as shown in this beautiful movie, it can actually fundamentally damage their self-assembly. So that's why the first few papers in my group really pushed the boundary of liquid phase TEM imaging to low electron beam intensity. And at that very low electron beam intensity range, we were able to successfully eliminate beam-induced nanoparticle reactions. So with this complication understood, in the recent self-assembly work of ours, as shown here, we were actually able to check single moving nano-sized particles in solution, resolving both their positions and orientations as shown in this movie. And in this example, we actually find out that self-assembly follows the quantitative laws of molecular polymerization, such as the step growth polymerization. So building upon this work, what I'm going to show you from now are two non-published systems, while liquid phase TEM to us is no longer just a fancy tool to study mysterious dynamics unique to a confined beam-intensive environment. Instead, it can really be related to practical experiments outside TEM. It can validate established theories and really provide meaningful guidance on our experimental efforts. So our first system is charged gold triangular nanoprisms, as shown here. The length is about 100 nanometer and the thickness is about 7 nanometer. The surface is coated with charged thiols, so when they're dispersed in water, they can interact by van der Waals attraction and electrostatic repulsion. There are two reasons I choose to study them. The prisms that are self-assemblies are very useful. They have special plasmonic coupling properties for applications such as nano-antenna arrays, which can locally concentrate electromagnetic fields, and they are also highly anisotropic in shape. So we were just curious how the shape anisotropy will induce interesting self-assemblies. So on this slide, I'm going to show you, after all the lessons we learned, a liquid phase TEM movie of the self-assembly of prisms for their individual self one by one, which is not the ensemble measurements such as X-ray small angle X-ray scattering measurements can do. So we first loaded an aqueous solution of individual prisms into TEM, and then we triggered the self-assembly by increase in salt concentration, which screens the electrostatic repulsion. So you can see, first, There's a cloudy solution with dark shapes flying in and out, and that's already very amazing because that means the nanoparticles are actually moving very fast as predicted by Brownian motions in solution. And gradually you can see a very ordered hexagonal lattice emerges from the disordered structure. And that was extremely exciting for us because it's still the first time people see nanoparticle superlattice formation in solution in real space and in real time, not just some disordered blobs. But at the same time, if you look at this movie for several times, you might actually get confused, just as we were. We started from triangles, so why the dark shapes here actually look so circular? And why do we have a hexagonal lattice symmetry out of triangles? So those questions actually bothered us for quite a long time. But fortunately, liquid phase TEM allows direct imaging, so we were able to see traces of first individual prisms sitting flat on the substrate, and then another prism fly in and stack onto the original prism not perfectly in registry. And this misalignment can actually add up so that we start to see more and more circularly shaped projections in TEM. So this is when we realized we're not really looking at the individual prisms now. We're looking at a 3D lattice. As you can see in this schematic, individual prisms first pack face to face into columns, and then the columns assemble further into a hexagonal lattice. And even after equilibrium, they're still quite dynamic at the lattice site, vibrating due to thermal fluctuations, and breathing following interesting vibrational modes as a way to dissipate energy. So you might wonder if this involves very complicated interactions, or if the self-assembly is driven by thermodynamic equilibrium. My old friend, Eric Lawton at Northwestern, and his student Zui Wang were actually able to reproduce the same type of 3D lattice for Monte Carlo simulation. So as shown here, the color here from green to red really shows a steady increase of structural order here. And in this movie, only van der Waals attraction and electrostatic repulsion are evolved. And towards the end of the movie, you can actually see the equilibrium columns do include misaligned prisms, consistent with our experimental observation. So up to now, I have shown you that we have observed the formation of a very novel hierarchical lattice, and now comes to the real cool part of the system. From the experimental TEM movies, we can actually study something that is missing in the simulation, the real-time crystallization kinetics, or the existence of intermediates. In simulation, those details were hard to probe because it's too expensive to compute a large system with a lot of particles interacting with each other, and at the same time actually concerning all the nanoscale morphology details. So here I'm playing the TEM movie of the observed crystallization process. On the left is a TEM movie with single columns checked as the green dots. And then on the right, we show based on the positions of the columns, we can perform the binary cell analysis and determine the bound connection network. So the color of each binary cell here really signatures the number of nearest neighbors surrounding each column. And my student Zihao, whose photo is showing here, is really the intelligent drive and intelligent coder to really behind this effort to teach computer to do this large-scale automated tracking. So now that we have this bound connection network, we can calculate two order parameters to describe a single column. One is the local bound orientation order parameter, which tells how ordered the column is, and the other is the local density of a single column, which describes how dilute or concentrated the surrounding environment is. And because we have a movie, we have a lot of columns, and in the end, again, experimentally, we can plot out this probability map of columns in this two-dimensional order parameter space. So if you look at this 2D map here, your eyes can actually pick up two states, as the red color really represents more populated states. And surprisingly, apart from the highly ordered, high-density state, which is essentially our final crystal, we can also see another state of high density but low structural order. And this is our intermediate. This is the intermediate people have predicted in theory, and we're able to recapture it. We will refer to them as the liquid and solid states because their structural features, the radial distribution function, really resembles those for liquid and solid phases in atomic systems. And then we can come back to real space snapshots connected from the movies. You can see clearly that before nucleation, the system is very dilute, which is we label here as yellow. But then the particles began to concentrate locally, and the dense liquid-like states start to appear as labeled in blue here. And then as the growth of the disordered blue domain, some crystallized labeled as red start to renucleate from within until it fully converted to the crystalline region. So in other words, this crystallization is a multi-step process with a dense amorphous liquid state as intermediate. And this is repeatedly so in multiple movies as what we show in this master curve. And I like to comment, such multi-step crystallization actually has been characterized in protein crystallization before, possibly because very similar building block size and interaction ranges. So before we move on, let's actually reflect on what we learned. For a long time, regarding transition pathways or reconfiguration of smart materials, different people actually use different terminology in different fields. The standard model system are micron-sized colloids. So you can read statements like, they're good because one can see their size, shape, motions directly one by one, and optical microscopy even in the most recent high-profile papers. And now what we know is we can push the size of model systems to nanometer. We can access to a lot more complicated processes, such as a 3D hierarchical crystallization. We can map nanoscale interactions, and we can validate speculations existing in literature. And eventually, maybe we can even make tiny nanomachines, and we can actually really show how they can reconfigure, how they can transform according to its local environment, just as shown in these video clips here. So this is all very nice, and then one day, I overheard the conversation between my student Zihao and the other student, Bingbing, his photo showing here. So Bingbing made this comment, well, it's certainly cool to have a hierarchical lattice. The triangular symmetry of the prism is actually got smeared out due to this random orientation. So how about we actually study a system where the nanoparticles themselves, rather than their self-assembled column forms, are the actual building blocks for the final superlattice. So that conversation really serves as the beginning of our second story. As you can see from the TEM image and the schematics, now the nanoparticle facets actually curved inwards. So each concave cube here still has the same coordination symmetry as conventional cubes, but they no longer have the large flat facets that can align in parallel. So as a result, their face-to-face van der Waals attraction, the attraction that was able to essentially lock prisms into columns, is much smaller here. So we note a dispersion of concave cubes inside the liquid phase TEM chamber, and here's the first type of this type of TEM movie. So the very beginning is very cloudy, very blurry, and in retrospect, I really appreciate Bingbing's patience to continue the observation. And then you can see lattice pieces appear in the view, and finally, you can see a big lattice formed and oriented parallel to the substrate so we can actually see through. Based on the fast Fourier transform, this is a simple cubic lattice consistent with what we would expect for the cubes. However, the crystallization process, namely how the front of the crystal expands, is actually not expected. So in this movie, we can follow single cubes as they come. The top crystal front was labeled as yellow and connected by red lines. And during the crystal growth process, you can see incoming cubes will first complete one layer completely and then grow another layer. So you don't see awkward protrusions, and this is the so-called layer by layer growth. And it makes sure the crystal has very flat and smooth surfaces as it grows, and this is actually a medium surprise. So to just put it into context, in almost all the previous colloidal crystallization, whether it's the big micron-sized colloids observed by optical microscopy with the nanoprisms we observe in our first story, their crystalline front is always very rough, as highlighted in the green lines in this movie. There are even theories based on capillary waves to quantify the fluctuation. So the layer-by-layer growth was also a puzzle for us. Unfortunately, we can track single particles and back out the energy landscape over the crystalline surface. So in this movie, the cubic crystal is already formed, yet the surface particles slide on the surface, sometimes individually and sometimes all together, with their trajectories labeled with time-lapsed color. And then based on the particle positions and the Boltzmann distribution, we can actually obtain statistically how the relative free energy oscillates along the crystal surface as shown in this graph. Now again, this graph is experimentally measured. So there are two conclusions we can obtain. First, the cubic lattice size are highly favored, corresponding to the valleys in this energy landscape. And second, the barrier between the valleys is actually sufficiently low, so cubes can quickly sample available sets to refine the final stable position. And interestingly, although we didn't find theories in colloidal science, this surface diffusion turned out exactly how atoms build into a faceted crystal as shown in these images here, but really pay attention that here, our building blocks are nanoparticles, not really atoms. So this similarity motivates us to re-dig into books on atomic crystallization, and our understanding truly gets improved when one day Bingbing actually came back from library with excitement. So he found this book, actually a series of books published in 1976, explaining the formation of the so-called atomic quasar crystal. So the right two panels are directly adapted from the book. On the top, when building blocks actually freely sample surface size, they might encounter kink, latch, and tear sites on a cubic lattice, and eventually form into the most stable kink site with the most coordinating number labels. And then as a result, there's this tendency to reform into one full layer before they grow another layer, which is consistent with what we saw. And if this conceptual analogy to atomic crystallization can work, the crystal surface can actually become roughened as shown here when the temperature increases, so the energy difference as well as the selectivity among different sizes are smaller. So we went ahead to retrieve this roughening transition in our superlattice composed of nanoparticles. Instead of varying temperature, we lowered the ionic strength, the salt concentration, and then we immediately observe a difference in the crystallization behavior. So as shown in this movie here, now the crystal front becomes extremely rough, with global formations of islands here and there. And moreover, this atomic analogy can be extended, so much like how atoms coalesce into crystals. In this TEM movie, the amorphous blob of cubes actually gets digested by the other growing superlattice and eventually form into a huge crystal. Again, a phenomenon not really observed in previous colloidal crystallization experiments. And for the movie in the middle, the local small crystallites try to attach with each other in an oriented manner so as to pack into a big crystal. And the last movie, at the first glance, almost looked like a 3D atomic twin crystal, although here each dark point or red or white point is actually a single particle, not really an atom. So it's possible that the fundamental colloidal interactions at the nanoscale mimic more of an atomic bond. In other words, although our particle interaction does not have the complete quantum feature of atomic bonds, their organization into a superlattice resembles that for an atomic crystal. And we find this connection across scales very inspirational, and there's a large space for more shapes, for more systematic studies to re-verify. So this is about the phase transition dynamics or reconfiguration dynamics of nano-sized objects in solution. And then my PhD student Johnny Smith joined the group, his photo showing here. He actually likes materials softer than inorganic nanoparticles. He reads biology and gets fascinated with this concept of morphogenesis. So morphogenesis describes how biological organisms form into different shapes, such as a crumpling of gas shown here. And in this part of the story, Johnny extends this concept into synthetic polymers, and the system we will focus on is polyamide filtration membrane, broadly used for water treatment. And this project is really only possible under the generous support from BP-ICAM. So here you can see a schematic of the polymer film, which indicates a very flat film. But if you zoom in with TEM, you can see the film actually has a lot of three-dimensional crumples and very rich nanoscopic morphology. So it actually has been shown that those crumples really determine solvent permeation and solute filtration. Yet, 3D imaging has been difficult, and that's because polymers are a lot more beam sensitive than inorganic nanoparticles. Electron beam, as shown in this movie, can actually easily drill a hole and completely damage the sample if you are not really careful. So in other words, even just resolving the 3D structure at the nanoscale directly has been an immediate challenge. Electron beam effect was a battle we fought really hard in our early nanoparticle self-assembly experiments. So we utilized all the lessons we learned and adopted the strategy of low-dose electron tomography. So tomography is a method which can detail a 3D shape by taking a series of 2D projections of different orientations. And clearly, as shown in these TM images, we didn't drill a hole this time, and we were able to actually achieve 3D reconstruction of the PA film as shown in this movie. So here, the red color fills fully reconstructed crumpled PA volume, and the cross-sectional view really shows there's actually a large void space enclosed by the PA crumple, and in fact, in our later measurement, up to 30% by volume is actually the void space. So I should comment that such tomography that resolves both the PA crumple and the void space in 3 dimension and nanometer resolution actually has been very challenging. So with this 3D tomograph, the convention in the field is to republish this beautiful structure, and frankly, I was tempted to do so too. But Johnny was greatly inspired by the work of our colleagues in medical science, so he got me educated on how a 3D scan image of brain tissue can be thoroughly analyzed and quantified to reveal all the metrics for diagnosis and therapy. So we adopted the whole methodology there to proceed one step further, to do a crumple by crumple morphometry to extract quantitative morphology details, which all turned out to be function relevant. So one thing you might have already recognized is that the PA crumples look overwhelmingly complex. So the inorganic nanoparticles we previously studied are very monodispersed and well-shaped. Our crumples actually vary, seemingly almost completely random. So we have this one question phrased in this Anna Karenina principle. Well, every single nanoparticle is the same. Is every crumple different in its own way? Our clue to answer this question is by adopting the beautiful morphometry analysis I have shown previously from bioengineers. So here, each crumple can actually be triangulated into a network of triangular meshes and generate the corresponding local maps, color-coded according to the curvature values. And next, for arbitrary 3-dimensional shape, they can actually be seen as composed of 4 types of surface elements based on the curvature values, such as tips, tubes, saddle points, and the completely concave regions. So in the context of water filtration, such surface elements really determine the local solute and membrane interaction environment. For example, for solute at the same distance away from the membrane, a concave surface actually has much larger interaction area than the convex ones. So as a result, we measured the distribution of the 4 surface elements in 15 crumples. And interestingly, they consistently fall into 3 types as shown in this graph here. So when we look back on the crumple shape, here with the color denoting the surface elements, we can recognize the general trend. So the domed crumple is essentially a hemispherical shape. The dimple crumple has the films curved inwards, And then the cluster crumple has a lot of saddle points to continuously connect the convex and concave regions. So in other words, the crumples are not each different in its own way out of the otherwise overwhelmingly heterogeneous crumples. After quantification, they only fall into 3 groups, and that's the first surprise. And next, we measure the local thickness of the crumple, which is the effective solvent permeation length. And this measurement can only be done with both the crumple and the void space resolved, not really possible with techniques such as atomic force microscopy. So as defined here in this schematic, the local thickness of the work cell point is essentially the diameter of the sphere containing the point and staying within the crumple. And this movie on the right really shows a 3D crumple color labeled according to the local thickness values. So we apply this analysis to the 3 groups of crumples we identified. And interestingly, the dimpled and cluster crumple actually has this bimodal distribution in the local thickness. And the second peak position has doubled thickness of the first peak, which really indicates the thicker region is essentially 2 thin regions physically touching each other. And this is also verified in this Z-scan of the 3 types of crumples, again consistent with a simple crumpling mechanism to reproduce such complicated 3D morphologies. And beyond mapping local features, our last analysis concerns the topology of the crumples by mathematically thinning a 3D volume into skeletons with nodes connected by branches. And here the numbers of nodes and branches really quantify the complexity of each crumple as shown in the diagrams, which again remain consistent with each crumple type. So for this part, what we learned include first the concept of morphogenesis for synthetic polymers. And now that we can quantify the nanoscale structure very thoroughly, we actually have a new perspective of the filtration membrane, this triangle relating synthesis, structure, and performance. And indeed, as we previously hypothesized, different synthesis conditions based on the same chemical reaction can render very different topology of the crumples, as shown in this matrix of TM images. And as to the relation between structure and membrane function, we conducted a model absorption test. In particular, we immerse our membrane in the same concentration solution of model solute, the heavy metal elements such as lead and zinc. It turns out they spatially distribute very differently upon the crumples. Zinc can actually penetrate deeper, while lead kind of gets blocked at the crumple surface. So this probably has relationship with the hydration energy, which is under our current investigation now. Of course, this triangular view of soft materials and the methodology can also apply to other systems, such as polymer films in photovoltaic applications, iron sulfide scale, or even asphaltene aggregates. So with the knowledge and skills on these previous 3 types of synthetic systems, we only become even more ambitious. So as I showed at the very beginning of my talk, the ultimately important nanoscale dynamics actually concerns the cellular machineries moving vividly in living cells. So as a result, 2 recent Nobel Prizes were given to direct nanoscopic imaging techniques relevant to biological systems. One is cryo-electron microscopy, and the other is super-resolution optical microscopy. So yet out of our full respects to these 2 winning techniques, we see a disconnection, and that disconnection is really the motivation of our work. So for cryo-electron microscopy, it utilizes the Angstrom resolution enabled by TEM, and in order to maintain the latent morphology of proteins in liquid, they're usually vitrified into a solid state. So one can get beautiful resolution 3D shape through single particle analysis and reconstruction. But the samples are vitrified. They are only snapshots without dynamics. One cannot really study the motions, interactions, self-assembly, or just an in situ response to external stimulus. On the other hand, for super resolution optical microscopy is compatible with a liquid sample, but it requires fluorescence tag It uses a point spread function fitting to achieve tens of nanometer resolution. It does not resolve the real nanoscopic morphology, which is actually crucial to protein function. So as a result, computation still dominates when it comes to the single-level protein dynamics. So the merits or drawbacks of these two techniques makes these two techniques belonging to two different fields. Cryo-EM focuses on structure. It belongs to the field of structural biology, while super-resolution optical microscopy concerns the physics behind their dynamics. It belongs to biophysics. So our dream here is to combine the merits of both techniques to work along the line of structural biophysics to reconstruct the elusive at the nanoscale, being able to see both the nanoscale morphology at the best possible spatial resolution and also the in situ dynamics in the native liquid environment. So that's our dream. And I'd like to re-emphasize this extension from artificial materials to biological systems is actually a big jump. Proteins are more sensitive to imaging electron beam. They are composed of low atom weight elements such as carbon, hydrogen, sulfur, so the inherent TM contrast is lower. And more importantly, they tend to be very irregular in their shape and surface chemistry. So as a first step towards the dream, we choose to focus on membrane proteins, proteins that are positioned and function adjacent or across a cellular membrane. Those protein membranes are widely relevant, critical to govern information and mass flow across cellular membranes, and serve as more than 1/3 of disease targets. They are very large in size, so good to have sufficient TM contrast. They lead to stay in lipids. So even just that structure has been very difficult to resolve using conventional techniques such as solid-state NMR because they are too large to analyze, or to use X-ray crystallography because of bulk crystal forms of these membrane proteins are actually isolated from the lipid bilayer, the cellular membrane. So with all those difficulties in mind, I'm going to show you our efforts of imaging membrane protein structure and fluctuations in native liquid and lipid environment using TEM. I'm going to share with you the first-hand lessons we learned as well as the success we have achieved. Our system is nanodisk. So this is a technique developed in the molecular biology department of UIUC. And we have a collaborator, Professor Aditi Das, to retrain and teach us on the sample preparation. So shown in the schematic here, a nanodisk actually includes 3 components. The membrane protein of our interest in the middle, wrapped by rafts of lipid bilayer, much like how they sit through a cellular membrane, and then with a membrane scaffold protein to recircle the lipid bilayer to make sure it's stable. I'd like to comment here that those 3 components are all put together due to non-covalent interactions through self-assembly, and using this nanodisk structure, it can make sure that membrane proteins are stable in solution. They can stay in the native lipid environment, and at the same time, they can be easily processable in the form of a colloidal particle dispersion. So in particular, we first use a membrane protein cytochrome reductase, and I will refer to it as a CY protein from now on to redevelop sample preparation and imaging protocols. And this, showing on the right, is actually a conventional dry TM image of the sample, with the liquid lactively stained with uranium acetate. So here the whitish contrast is actually from the CY protein, and it matches really well with the dimension we expected from the sample preparation. And then given this sample, we went ahead to really load it into our graphene liquid sandwich I mentioned to you earlier. As shown in this schematic, a graphene sandwich is actually made by first transferring graphene onto a metallic mesh TEM grid, and then deposit the liquid sample and cover it with the other TEM grid to reform a liquid sandwich. The van der Waals attraction between the graphene layers can seal the pocket really against the high vacuum condition of TEM. So this is a method that has made many successful metallic nanoparticles. For example, here is a liquid phase TEM movie where we can track both the rotation and translation of a DNA gold nanoparticle cage. However, when we just attempted to sandwich our nanodisk solution, this image on the right is what we saw. There is both a good news and bad news in this image. The good news is under no acceleration voltage, we're actually able to resolve the generic TEM contrast of the nanodisk in the absence of staining agent. The dark shapes showing here should be our nanodisk sample. And the bad news is the nanodisks look very distorted, and we actually repeated the same procedure for over 3 months, and eventually we realized this is because TEM grades made out of metal are rigid. They cannot really conformally cover a huge liquid pocket, but only a small liquid pocket. While the small liquid pocket is actually good enough to see nanoparticles of 5 nanometer in size, it can easily squeeze apart the assembled nanodisk into collapsed shapes. So to overcome this issue, we actually have to have a personalized imaging method for our nanodisk sample. And as shown in this schematic, we also started from depositing a tiny droplet of sample liquid onto a graphene-coated TEM grade. But then instead of covering the sample with another rigid TEM grade, we cover it using a free-floating graphene on the air-water interface. So shown in this photo, the grayish film is actually a piece of graphene which can be picked up due to surface tension. So in this case, the floating graphene is actually more flexible than the rigid grade and can easily cover a large liquid pocket wall. And then based on this method, we got a liquid phase TEM movie. It's actually the first ever TEM movie of a moving and fluctuating protein sample of a nanodisk. Here the black feature is a nanodisk. You can actually see it's moving and rotating freely in solution, exhibiting a disc-like shape as your eyes do the 3D reconstruction for you automatically. And on the right is the processed movie where we only kept and monitored the nanodisks with both the central mass and also the surface contours tracked and overlaid together. The nanodisk is moving, their projections are changing because they're rotating in 3 dimensions and also because they have fluctuations. So when we view a nanodisk that is largely sitting flat, we can see the fluctuations in the XY plane more obviously from this movie, synchronizing the TEM observation and the measurement of the disk dimension. On the right, when we deliberately design a much larger disk, not only does the size consistently become larger in terms of our feature we observe in TEM, the fluctuation also exhibits more possibilities, including the eventual figuring dynamics that is really shown in this movie. And we really see this system as a seed for many emerging possibilities we can extend to other very hard to resolve proteins and going beyond just structuring dynamics or fluctuation dynamics. We are also pushing towards functional dynamics, dynamics of the structure change that are really associated with a biological function and also triggered dynamics. So as a summary of our theme, we can now actually see new materialized opportunities when electron microscopy meets soft materials. And for the first part, on the aggregation of nano-sized objects, going beyond the inorganic nanoparticles we have shown, we can actually extend to something you might be more familiar with, the asphaltene aggregation, which is again a BP-ICAM collaboration with Professor Grisberg at Manchester. So we can look at and image the aggregation dynamics in real space, in real time in the solution. We can actually extract aggregation laws together with the element mapping of the aggregates. And the concept of morphogenesis of synthetic materials can also go beyond polymeric membranes and apply to other hybrid nanoparticle systems. I've shown you the single membrane protein imaging. I'd like to comment going beyond just single proteins, we're now also looking at aggregation of many proteins interacting with each other in the solution environment. So with that, I'd like to first thank BP's support, especially my BP mentor, Dr. Matt Kuzik, who is really always a great person to talk with on all types of scientific questions. I'd like to end my presentation with these 2 photos here because it's actually very special. So on the left is a photo of a mountain where everyone can easily obtain. And it's only when someone actually get into the mountain and use light to reshine on the wall, that's when they can see beautiful artwork. And that's really the power of using a direct imaging method at a resolution that was not really accessible before. I'd like to really thank my group. I'd like to thank you for all your attention. I'll be happy to take questions from